What is going on, guys? Welcome back to the Python data structures tutorial series. In this video today we're going to implement the trie data structure. So let us get right into it. Alright, so we're going to implement the trie data structure from scratch in Python today, and as always I want to start by giving you guys a brief explanation of the data structure in theory here before we get into the coding. And as a side note, for those of you who are interested in that, the data structure name is written like this, T-R-I-E, and it actually comes from the word retrieval, which means that the original correct pronunciation would be tree. Now, why do we call it trie? Mainly to distinguish it from the concept of a tree, especially because the trie is also a tree. It's a tree data structure, which means that if you just say, oh, we're working with a tree, we don't really know what we're talking about. If I say I'm working with a tree data structure, so we're calling it trie mainly to distinguish it from the tree, to know it's not just a tree, it's a trie. That's the only reason why we pronounce it that way. Actually, it would be pronounced tree because it comes from the word retrieval. Just as a side note here for those of you interested in that. But let's take a look at the data structure itself. What's the idea behind it? It's a tree, as we said, and it's very useful for working with strings and primarily used for things like auto-completion or having a dictionary, for example. And the idea is the following. We have a root node, and every node has two things: a dictionary of children or of child nodes, and a flag saying if this is the end of a word, yes or no. So we're going to say that if a node is the end of a word, we're going to write end in it. Otherwise, I'm going to leave it empty. So this is the root node now. It is not the end of a word, and our trie is empty. Now, let's say I want to insert a word, for example, hello. How would I do this? Now, what happens here is I go letter by letter, and I insert the word into this trie data structure. So right now, the root node doesn't have any child elements. So what I do is I'm looking for h. H doesn't exist, so I'm going to create a new key value pair where h is the key and h points to a node. And this node now has, again, its own dictionary and can be the end of a word or not. Now, it's not the end of a word, so we're going to continue. Next up, we have E. E is not part of this node or of this dictionary, so we're going to add it. E points to the next node, which again has a dictionary. Here we're going to do the same thing. L points to the next node, has a dictionary with another L, points to the next node, and this one has a dictionary with O. And then this O points to a node which has an empty dictionary and is the end of a word. This is how we would insert hello into our trie. So we have the root node with the dictionary. The H points to a node that has an E, pointing to a node that has an L, pointing to a node that has an L, pointing to a node that has an O, pointing to a node that right now is empty and has the end flag set to true. Now, we can also import or insert another word, for example, minimum, like this, minimum. And we could see what happens here. Now, there's a reason I choose this word. I'm going to show this here in a second. But let's say, now I'm not going to use the dictionary notation here. I'm just going to use connections, but it's the same idea. The M is pointing to a node, which is pointing to, which has I pointing to another node. N, I, M, U, M, and end. So why am I using this word? Because there are a couple of words that are quite similar, and we're going to see what happens, for example, if I now insert the word minimal, like this, minimal. What happens in this case is if I want to insert this word, I go M, I, N, I, M, and then I see that here in this dictionary, this node here has the dictionary U that points to this node. And what I do now is I add another key value pair. So I say A, which points now to another node. I'm going to do it like this. So I'm going to just say we have another branch here, A, which goes to another node, which goes using L to another node, which is also the end of a word. And now you can see they have the same prefix. By the way, this data structure here is not just called trie, it's also called a prefix tree. This is also a way to refer to this data structure, a prefix tree. And the reason for that is you can see M-I-N-I-M, minim, is the prefix for minimal and for minimum, which can be useful again for auto-completion. Now, another thing that we can do is, let's say I want to insert the word mini. What happens in this case? Well, in this case, all I have to do is I have to go M-I-N-I, and then I have to set this to end. Now, end doesn't prevent my try from going further, so I can still go to minimal, but it says that this is the end of a word. It doesn't have to be the end of the search, but it is the end of one word, so mini is actually a word. And this can be useful now because if now I ask, okay, give me an auto-completion for MI, I can efficiently find mini, minimal, and minimum. And I can extend this, I can build a dictionary like this, I can have certain keywords like this. This is a very useful data structure, and this is what we're going to implement in Python from scratch today. So let us get started. I'm already in my current directory. I'm going to delete everything that's in here. Actually, we don't have anything in here. So I'm going to create a new file. I'm going to call it trie.py. And we're going to have, of course, a node class. So class node is going to have a constructor, and it's going to have self.children set to an empty dictionary, and or actually I'm not sure if this is an empty dictionary or a set, so let's actually say dict like this, and then we're gonna say end of word, or actually let's call this is end of word is equal to false by default. That is our node. That's about it. And then we're going to have a class trie. And this trie is going to have an init method. And in this init method, we're going to initialize the root node. So we're going to say self.root is equal to node. All right. So every tree is going to start with a root node that has an empty child dictionary and is not the end of a word by default. Now, let's define again what kind of methods we're going to implement for this data structure. We're going to have an insert method, which is going to allow us to insert a word into the trie. We're going to have a search method, which is going to tell us if a given word is part of the trie. So, for example, in our tree here, if I type mini, I'm going to get true. If I type minimalistic, I'm not going to get a true. I'm going to get a false. That's the basic idea here. Then we also want to have a delete method so that I can remove words. How would I do that in theory? Of course, I would just remove the end flag if I remove mini, for example. So if I remove mini, I would just set this to false again. If I remove something else, I also delete the nodes and the connections. We're going to take a look at that when we get to the implementation. Then we also want to have has prefix. The basic idea here is that we check if the prefix is part of the tree or not. And then we also want to have two a little bit more, not necessarily complicated, but they're going to take more, they're going to have a higher runtime complexity, if that's the correct term, higher. But they're going to be a little bit more difficult, which are going to be the starts with method. So for this method, we're going to pass a prefix, and this prefix, or this method, will give us all the words that start with this prefix. So it's going to search the tree. And then we're going to also have list words, which is basically going to give us all the words of the dictionary, you could say. So we don't need a prefix for this. We just get all the words. And that's basically it. That is going to be our trie data structure. Now let us start with the insertion. We already talked about this. How do we insert? We start at the root node. We say current node is equal to root. And then what we do is we say for character in our word. So we go character by character. We say if the character is not part of the dictionary of the current node, so if we don't find the character as a key in the children dictionary of the current node, what we do is we say current node dot children, add this new add this character as a key and let it point to a new node that we create. And whether we had to create it or not, afterwards we're just going to say that the current node is going to be that node. So current node dot children C. So either it was there before, then we're just going there, and otherwise we're creating it and then going there. And we do that until we have no characters left in our word, and then what we do is we say current node dot is end of word equals to true. It's as simple as that. We just follow the path until we get there, or we have to create new nodes until we get there, until the word is processed, and at the end, at the node that we're currently at, we're going to just set end of word to true. This can be an already existing node, like it was the case for many. In this case, we just set it, or it was the node we just created. In this case, we also just set it. So the insertion is quite simple. We're going to talk about the runtime complexities later on. The search is also quite simple because we have to do basically the same thing, but instead of creating it, if we don't find it, we return false. So we say current node is equal to self.root, and then we say for character in word. If the character is not in the current node children, we're going to return false because we obviously don't have it. So if I get to a point where I have a character and it's not part of the children dictionary of my current node, it means the word does not exist, obviously, because the next character does not exist. So I'm going to return false in this case. Otherwise, I'm going to keep going down the line. So I'm going to say current node children C, move further, and in the end, we're going to say once the word is processed, we want to know the word or the node I'm currently at, is it the end of a word or not? So I'm going to return current node is end of word. Because of course I can find the term. For example, here what I could find is minimum without the M, so minima, like here, I could end up here, which would be a valid node, but I would not have it set to end, which means that I would get false here as a return. So that's that. Now, the rest is going to be a little bit more, or actually has prefix is kind of simple. So for has prefix, we can also do the same thing. Actually, I think we can just copy this. Actually, now I copied it to my to my clipboard. So let's go paste it down here. The only difference here is that we're going to return true every time. So it doesn't need to be the end of the word because we're not checking if the word exists. We're checking if the prefix exists. So if I end up at a node, I can return true. Now, the deletion will be a little bit more complicated because we need to define a helper function underscore delete. We're going to say def underscore delete. And this function will get parameters so that we can keep track of certain things. First of all, it will get the current node. It will get the word, and it will get the index so that we can recursively call it and update the progress, so to say. The idea is I'm going to call this function or this method in delete once initially, so self-delete on the root node. So I'm going to say self.root, this is the word that needs to be deleted, and I'm currently at index 0. So we haven't processed anything of the word yet. And in our delete method, this is going to be a recursive method, so it's going to call itself. We're going to have, first of all, some base cases for terminating. We're going to say if the index is equal to the length of the word, then we're done. And I basically just have to see, is this the end of a word? So if this is not, the current node is not the end of the word, we return false. Why do we return false? Because we don't need to do anything. We don't need to delete anything. This happens when the word didn't exist anyway. So we don't need to delete anything on the upper levels. We can just say, okay, if I'm ending up at a place that is not a word, I don't even have to do anything. So return false. The return value is important because we have to also recursively remove nodes if it's necessary. So basically, if I'm removing this here, I just need to set it to not end of a word anymore. So if I'm removing many. If I'm removing minimal, I have to remove this, I have to remove this, and also this connection here. So I have to remove more than just setting this to not being an end anymore. Unless I want to keep like this, or not even unless I want to keep the structure, I have to delete it because otherwise minimal would be a valid prefix, which it shouldn't be. So this is why I use the return values here. So if I end up at a place that is not the word, I just return false because obviously I'm not removing anything here. And then I'm going to say current node, in all cases, current node is end of word is going to be equal to false. Now, if it was false already, this doesn't change anything. If it was true, it means that I'm ending up at a place where this is a word, this is the end of a word, and it is set to true. So I'm going to set it to false now to say this is no longer a word. I'm removing it from the dictionary, so to say, from the trie. And then I want to return here length of current node dot children is equal to 0. If that is the case, I want to return true. So if I don't have any child nodes at the current node, I can return true because that means I can delete other nodes as well. Whereas if this has child nodes, I cannot just delete everything because there are other words that would be impacted by it. So I return true, which means you can delete the node if this node doesn't contain any child nodes. So that's the base case. Otherwise, what we're going to do, or not just otherwise, or actually otherwise, yeah, because we return if we get to the if statement. Otherwise, what we're going to do is we're going to say the character is the word at the specific index. Remember, we're passing the index here, or we're going to pass the index here recursively when we call the delete method, but by default or in the beginning it's 0. So we're getting the first character or the character at the index. And then we say node is equal to current node children get C. So from the current node, I'm looking at the child dictionary. I'm getting the node that corresponds to the key C. Now, there is the case that this node does not exist. So if, or this key does not exist. If this is the case, this is going to return none, and I can return false because the word doesn't exist. If the word does exist, what I do is I delete the current node. How do I do that? Or I don't delete the current node. I call recursively the delete function, but I have to store whether I have to delete the current node or not in a variable. So this is why we need to return values. So we say delete current node, you could imagine a question mark here, is equal to self._delete, calling it on this next node with the same word and the index increased by 1. So what this means is we go one node forward and we also increase the index by 1 so that we can continue the same process down the line. And this is going to recursively return true or false. And if it returns true, it means that I can delete the current node. If it returns false, it means that I'm not going to delete the current node. So at some point, this is going to return finally. And then I want to know if delete current node. What I'm going to do is I'm going to delete current node children C. And I'm going to return also here for this node, if the length of the current node dot children is equal to 0, and also the current node is not end of the word. So basically, I get the instruction delete this node, and then I delete this node from the children. And I also say for this node, delete it if it has no children, or if it's not the end of a word, so that we can recursively delete all the nodes that are no longer necessary in our trie. I hope this was not too confusing in the explanation. The basic idea here visually, again, let me show this, is for some nodes, when you want to delete the word, like mini, all you have to do is you have to delete the flag that it's the end of a word. You don't have to remove any other references here because it has child nodes. But for example, if I remove minimal, this doesn't have child nodes. So I can remove this node. I can remove, of course, the flag. I can remove that this is the end of a word. but I also don't have children, which means I can remove this node. Which means I can remove this node because it then also doesn't have any children anymore, which means that this connection can also be removed. But then, of course, this should not be removed because it does have children. It does have minimum. Another word that is also part of our try. So I hope this is somewhat easy to understand here why we're doing it that way. Even though the recursion might be confusing, but we're basically returning, should you delete me or should you not delete me? That's the return value. All right, so that's the delete method. And now for the starts with and for the list words method, we're going to use a depth first search, so a DFS algorithm. The basic idea is you want to go to a certain prefix and then you want to get all the child words, so not just the nodes, but the words. You want to explore all the child nodes to find words and you want to collect them in a list. So we're going to say words is equal to an empty list, and we start again at the root node. And then we say for C in prefix. So we want to go to the position, and we want to say if C not in current node dot children, we're going to return an empty list, or actually we can return words because it's going to be an empty list at this point. But if we don't get into this if statement, we're going to just go further and further. We're going to say current node is equal to current node children C, which means we're going to go to the prefix. For example, if my prefix is M, or if my prefix is mini, or let's say min, I would go to this point here, min. This is where I'm at now. And from here, I can start a DFS. So I can go like this and then like this. So a depth first search. All right, so once this is done, we're going to be at the position of the last prefix character, and then we're going to define here a helper method, which is going to be it's going to be a nested method inside of this starts with method, and I'm going to say underscore DFS is going to get a current node and a path. The path is important to be able to reconstruct the word, and this is going to recursively call itself. So we have quite a bit of recursion today. Basically, the idea is if the current node is the end of a word, we want to store it. We want to add it to our words list here. So if we end up at a node that is the end of a word, what we want to do is we want to say append to the words list the path. And the path is going to be a collection of characters. So in order to get it as a word, we need to join it. So we're going to say join, not word, sorry, path. So the path is going to be what we recursively pass here to the function call. So if we are at the end of the word, get all the characters, join them together, and append them to the words list. And then we're going to say for C child nodes in current node children items. So basically for the key and child node, C being the character that performs the transition, child node being the node that the transition is performed to, we're going to say DFS, go to that child node and say path plus and then list C. This is important that it's a list because we're extending an existing list. So this is the list of characters that we have. We collect all the characters, and at the moment we arrive, or the moment we arrive at the end of a word, we collect it. And of course we need to call this method once. We need to say DFS current node here, and we start with a prefix. This is important because you want to not start with an empty list. You already have the beginning. For example, min is already part of the word, so you want to append to it. In our example, I can show you that. What we want to do here is we want to go to this position, to min, and then what we want to do is we want to do the DFS. So we want to go down. Oh, here's the end of a word. So what I do is I have now M-I-N-I, and I want to join them together to mini and collect them in my list of words. Then I go deeper, I say M, then I say A, L, O, end of word, perfect. So I can say now, I have M, A, L, join them together, minimal. And then I also have here a second call, of course, U, M, O, end of the word, okay, this is minimum. So I found all the words that have this prefix, that start with min. And of course, what I need to do in the end is I need to return the list of words. All right. Now, list words is basically a similar approach, only difference being we don't need a prefix. So what we do here is we say words is equal to an empty list. And we say, again, DFS. We're going to have a current node and a path. Actually, I think this is the exact same implementation. So I'm going to just copy this. And we're going to say that the only difference is that we're calling this DFS now on self.root with an empty list as the prefix. And then we say return words. That's it. Now, if I didn't make any mistakes, which would be surprising as always, that is the try data structure. So I'm going to write some test cases here just to see if this works. And then we're going to talk about the runtime complexity. So if name is equal to main, what I want to do is I want to create a try. And actually, let me think about this. I'm going to just copy paste what I have here in my prepared code, so that we don't have to, actually this was not the correct key. Let me just do it like this, there you go. And what we do here is we have basically a try, we insert hello, Henry, Mike, minimal, minimum. Let's also insert many. And then we have, or actually I'm inserting mini down here, so let's remove it here. Let's run this code to see if it works. No, it doesn't work. Key error H, perfect. This means that our insert method probably doesn't work correctly. So what's the problem here? Oh, I found the problem. It's that we're missing a not here. Of course, you want to create a new node if it's not in the children. You otherwise want to just go to the node. But if you don't have the character already in the list, then you want to create a new one. Otherwise, just jump to the existing one. That's the problem. We have another problem, which is name word is not defined. So where is that again? This is in has prefix. Oh, is this because we're lacking a parameter? No, actually has prefix is fine, but we need to say prefix. And now it should work. Okay, let's compare the code, or let's compare what it should do. We insert hello, Henry, Mike, minimal, minimum. We can print that, we get it. This is from list words, so this works. Then we say has prefix. Actually, what we're asking for here is mi. It has it. If I say starts with mi, I get Mike, minimal, minimum. If I say delete minimal, and then I do starts with mi again, I get Mike and minimum. Then I search for certain words. I search for minimum, minimal, and mini. I get, in this case, true, false, false, because I removed minimum. And then we insert, or I removed minimal. Then we insert mini, and then I say starts with mi, and I'm getting Mike, mini, and minimum. So as you can see, this works. And now let's talk about the runtime complexity. How difficult is it to do that? Well, for the insert, we have O of m, so linear runtime complexity, where m is the length of the key. So actually the length of the word, we could say. So depending on how long the word is that we're inserting, that's what determines the runtime complexity. It doesn't matter how large the tree is. It doesn't matter how many words are already in there. It matters how long the new word is that I'm trying to insert. O of m, where m is the length of the word. So it's linear in terms of word length. When it comes to the search, it is basically the same. O of m. Actually, let me just copy that. Because what do we need to do? We need to just go and look up the characters and go to the next node, and next node, and next node. Now, of course, we can terminate earlier if we see that the first letter is already not part of the try. Then we can, of course, just terminate. But in the worst case, we have O of m, which is the length of the word itself. So then the same is also true for deletion. O of m in this case. Actually, I wanted to paste this here again. And for has prefix, we also have O of M, but for the other one, for the starts with and for list words, we have different runtime complexities. For starts with, we have the following. We have O of M plus K, where M is the prefix length and K is the total number of characters in all suffixes. Basic idea being I definitely have to go M because I have to go to the note where the prefix ends, so that's for sure. And then I have to go to all the characters in all the suffixes. So for example, in our tree, in our try here, we definitely have to go to min, but then I also have to go to IMAL, MUM. Now, the thing is, if they overlap, I can save certain things. So for example, if my prefix is M, then I, N, I, and M overlap. So I only have to count them once. So I don't actually have to count all the words lengths, because then I would have I, N, I, which would be 3. I would have I, N, I, M, A, L, which would be all of that. And then I would add all of these together. If I have overlaps, this results in much less characters that I have to count, because if they only differ in the last couple of characters and I have huge words, that's going to make a difference. But in the worst case, I have O of M plus K, where M is the prefix length. That's how far I have to go for sure. And then K depends on the overlaps, but K would be the total number of characters in all suffixes. And then we have also list words, which is easy to denote. It's just O of N, but N is the number of notes in the try. We have to go through every single note in order to list all the words. So depending on how many notes you have in the try, that's how many notes you have to traverse in order to list all the words. So yeah, this is how you implement the try data structure in Python from scratch. So that's it for today's video. I hope you enjoyed it and hope you learned something. If so, let me know by hitting a like button and leaving a comment in the comment section down below. And of course, don't forget to subscribe to this channel and hit the notification bell to not miss a single future video for free. Other than that, thank you much for watching, see you in the next video, and bye.